Hopefully this takes well today. All right, welcome back after the exam. You guys all survived. No one here had to stay away from ledges or sharp objects or anything, I'm pretty sure. Your results were good. I mean, they're never perfect, and everybody's always mad when they get it back. I can't believe I made that mistake, but overall, we did well. I'll talk about a little bit at the end when I give them back. Some of the things that easily fixable things, other things just you don't need to fix. I mean, it was, most people were right on. I want to do a couple problems from the weekend material because there are some problems that are a little bit trickier. If you don't have a lot of experience with factorials or with combinations or things of that nature, some of these problems can be a little bit more treacherous, let's just say. So I want to do a couple that are similar to what I'm asking you on the quiz that I believe is due tomorrow. One, I want you to consider a sequence B0, B1, B2, B3, and so on that's defined recursively as Bn equals 3 to the n minus 2 to the n. And that would be for all n greater than or equal to 0. So just to look at it, if that's what the sequence looks like, it's always a good idea to just jot down the first few terms just so you know you're on the right path. This will not aid you in finding an answer, but when you find an answer, it'll help you make sense of your answer because you go, yeah, it fits, right? We know that. We did that last week when we looked at some geometric and arithmetic sequences. Remember, we did the first few terms, say, yep, I think I'm doing it right. So if I just wanted to write down the first few terms, just say that many terms, what would B0, B1, B2, B3 equal?
0, 1, 5, 11.
All right, so 3 to the 0 minus a 0, and then the next one would be 3 minus 2, and then 9 minus 4, and then 27, 27 minus 8, and so on. Well, clearly, if you were looking at that, you don't see a pattern, do you? You see a bunch of random numbers, and that's okay. So what I want to prove that I could write this as recursively. This is not a recursion. This is the nth term. I want to write this as a recursion. I want to kind of work backwards and write it as 5 times the previous term minus 6 times the term before that for all k greater than or equal to 2. Now, I'm using a k this time. It doesn't matter what letter of the alphabet you use, right? Because I'm kind of defining it differently now. Now, the subscripts sometimes throw us for a loop. Well, all it means is that if this is a 2, then this is a 1, then this is a 0. That's all that means. And I can't go lower than 0, can I? So that's why k would have to start at 2. So then what's B3? Well, it should be 5 times B2 minus 6 times B1. So let's see if that actually works. Because again, we want to make sure that we believe this. I want to prove this. I first have to believe it's true. Remember that? So since we've written the first few terms out, let's see if that actually works, okay? So we'd be saying, according to this, that B2, which is 5, is supposed to equal 5 times B1 minus 6 times B0. Is that a true statement?
Yeah.
Okay, how about B3, which equals 19? That's supposed to be 5 times B2 minus 6 times B1. Is that true? Okay, that's not a proof, but do you believe it's probably true? Yeah, I'm asked to prove something's true. I checked it out for the first few numbers. Okay, life is good. This is not part of the problem at all. I always do this because I want to convince myself, right? For class, if I wrote the problem down incorrectly, could I have written this incorrectly? A plus sign rather than minus, switch my coefficients. Is it possible that I could mess up this writing it down? Absolutely. But by checking the first few terms, I'm convinced I wrote it down correctly and now I have something to prove. So now how would I prove this? That's not in question, by the way. This is not in question. This is the nth term. I'm trying to show that this works. So the easiest way to do that would be to start with, all right, according to that definition, bk obviously would be 3 to the k minus 2 to the k. What would be k minus 1 be? 3 to the k minus 1 minus 2 to the k minus 1. Yeah, exactly that. And what would this one be?
3 to the k minus 2 minus 2 to the k minus 2.
K minus 2. Okay, that, again, I'm not questioning that part. I'm questioning that part, okay? So if that is true, okay, now let's take, all right, so let's take this stuff here and see what happens when I try to put it into that formula. So let me take 5 times b k minus 1 and subtract 6 times b k minus 2. I'm going to just do this. In the end, what am I hoping I get? I'm hoping I get this. Agreed? I'm saying I want to prove the statement is true. I can't start by assuming it's true. You never start by assuming it's true, so I want to take this quantity here, manipulate it, and hopefully I get something that looks like bk. Again, a common error we often do is when I'm trying to prove a statement, I make my first step assuming that statement is true and then working backwards. Again, an absolute money-back guarantee. If you assume it's true, it will always be true. Anything you assume true, you're done. There's nothing left to do because it's true. You assumed it's true. No, your assumption, anytime you're doing a proof, whatever you're assuming is the law. It is the absolute fact. If I'm assuming a number is divisible by 4, then that's the absolute. That's the only part that can't be questioned is what you're assuming. That's why you can never assume what you're trying to prove. Because now it's absolute fact, regardless whether it's true or not. And that's a problem. All right, so when I put those numbers in, I'm going to go 5 times this. And then minus 6 times minus 2 to the k minus 2. Okay, now I need to manipulate this a bit. So it's messy. Now I'd really like to be able to combine the 3 terms and the 2 terms. There's 2 ways I can do that. One is I can make this 3 times 3 to the k minus 2 and make this one 2 times 2 to the k minus 2. Does everyone agree? I could do that. Or I could use the fact that 6 already has a 3 and a 2 in it, and when I multiply, I could beef these guys up to look like these. Does everyone see that? Both are absolutely correct. Which way do you want to go? Work this one down or beef this one up? Doesn't matter. Zachary, which way do you want to go?
I like the second one.
Beef it up?
Yeah.
Okay, so if I beef this up off to the side, 6 times 3 to the k minus 2, wouldn't this be 2 times 3 times 3 to the k minus 2? Which would be 2 times 3 to the k minus 1. Does everyone agree with that step? And then 6 times 2 to the k minus 2 would be 3 times 2 times 2, and then 3 times 2 to the k minus 1. Aha! So now I've got, I'll distribute the 5. I have 5 times 3 to the k minus 1 minus 5 times 2 to the k minus 1 minus that term, 2 times 3 to the k minus 1 plus that term. Everybody okay with that so far? I distributed the negative 6, and I got that term, and I got that term. Okay? Now, can I combine? I have 5 of them minus 2 of them. What does that give me? No, 5 minus 2. I'm adding them. So 5, 3 to the k minus 1s, minus 2, 3 to the k minus 1s. That would be 3 to the k minus 1s. I have negative 5, 2 to the k minus 1s, plus 3, 2 to the k minus 1s. I believe that would be minus 2, 2 to the k minus 1s. Yes? What do you think?
Just 3 to the k.
And how about the next one?
2 to the k.
And is that equal to the definition?
Yes.
Right? Great rejoicing, crowds dancing. confetti everywhere, right? Partying in the streets. That was the whole goal. My whole goal was to manipulate that and get that. Is that trivial? No, but it's not really hard either. So Zachary's suggestion of beefing up the second one by pulling 3s and 2s out, we could have just as easily said, well, I have 3 of these times to the k minus 2, and then 2 of these to the k minus 2, manipulating the coefficients, and guess what we would have probably seen? I would have had a 3 to the k minus 2 with a 3 squared in front. I would have had a 2 to the k minus 2 probably with a 2 squared in front. Right? Because it is true, I would have got the same answer. So this is how you would manipulate something like this. The only thing that we assumed was this, because that's the definition. We didn't assume this, we proved this. By taking, now we could have taken the right side and worked backwards, but that would have been way too much work. And you remember going back to baby trig, anytime you had a mathematical statement you're trying to prove it was true or verify it was true, you always took the more complicated side and tried to whittle it down and make it look like the easy side. It's really hard to take the easy side and work backwards and make it complicated. That's probably not a great strategy. I want to do a second one now that involves factorials because this may not be an area of strength, but coming really soon, we're going to be starting to manipulate factorials and things like that as a general thing. And there's something called the Catalan numbers. You don't need to know these. It's just a really cool, it's a cool definition, and it presents really great problems. Okay, the Catalan numbers are generated with the following definition. Okay, the nth number is 1 over, where's it, n plus 1 times that combination, 2n, choose n. Okay, these are called the Catalan numbers. So let's just write down the first few so we know what they actually look like. Because it sure seems like, well, these are all going to be fractions, aren't they? I mean, it seems that way because I'm multiplying by a fraction. Now, where can n start here? Well, we don't really have a 0 choose 0. That's not really a thing, so we kind of need to start at 1. Probably should write that. Okay, so if we're starting at 1, let's write down the first few Catalan numbers. So C1 would be 1 over 2 times 2 choose 1. C2 would be 1 over 3 times 4 choose 2. C3 would be 1 over 4 times 6 choose 3, and let's do one more. C4 is 1 over 5 times 8 choose 4. Now, if you have a calculator in front of you, these are ridiculously fast calculations. You just use your combination key. Small ones, maybe you know. Well, this means that's 1/2 times 2. 4 choose 2 is 6, so this is 1/3 times 6. 6 choose 3. Anybody know what that one is? 20. I'll let you calculate the next one. What's 8 choose 4? Again, just use your combination key.
70.
So what do you notice? These aren't fractions, are they? Because the factorial terms are going to be much bigger than the denominator in general, so they're going to generally encompass them. Okay, so this is an infinite sequence, goes on forever and ever and ever. Great. Okay, so what's the point? Because it's really fun to prove identities or prove results. So I want to prove, based on that definition, I want to prove that Cn can also be written as 4n minus 2 over n plus 1 times that. I want to prove this. I'm not telling you this is true. I'm saying I want to show that this is true. Now, I do one of two things. I can start with this definition, manipulate it, play with it, pull it apart until it looks like the right side. Or I can start with the right side, manipulate it, combine, do whatever until it looks like the left side. Which do you think is a better strategy? Starting with the left or starting with the right?
The right.
Yeah, you'd be hard pressed to undo the Cn definition. Be much easier to manipulate the right side with the factorials and then put things together. That's why I want to do this problem, because we are actually going to be doing a lot of this kind of stuff later on when we get to chapter 9. So, what is then Cn minus 1? What is this? Well, based on that definition, replace n with n minus 1. And what would you get?
1 over n.
1 over n.
2n minus 2 over n minus 1.
Choose n minus 1. Now, where would this have to start then? If the lowest if the lowest Catalan number would be a subscript of 1, if that's the lowest one, and I've got an n minus 1,
2.
then this would have to be,
Greater than
does everyone see that? That has to be n greater than equal to 2, because otherwise I'd be in a weird position here. Certainly can't start at 0. All right, so let's do this. Let's do this first. Okay, I really do want you to know the definition of a combination. You haven't done much. I asked you one problem, kind of simple manipulation. Well, if I don't get anything else right, let's get the numerator right. Okay, great. Now there's two terms on the denominator. One of them is going to be this thing factorial. We usually write that one second. And the other one's going to be 2n minus 2 minus this thing. What is 2n minus 2 minus n minus 1? It's just n minus 1 again, isn't it? Now, here's an easy way to know that you did it right. Add up the numbers on the bottom. What do they add up to? The one on top. So, for example, I did this during the test. If I was going to do 10 choose 7, that's 10 factorial over 10 minus 7, 7. 3 plus 7 equals 10. Okay, I did it right. 3 factorial plus 7 factorial is not 10 factorial. That's not what I'm saying. I'm saying just the two numbers. So it's like you're choosing this and you're leaving this many behind is the easiest way to think of this. So I know I did this right. So let's expand this. Well, actually, we're going to expand this in a moment. We won't do it yet. Okay. All right, so now let's take that whole quantity. So I've got, what have I got? I've got 4n minus 2 over n plus 1, and I am multiplying it by this. But we just said that's this. And then I have 2n minus 2 factorial. What do I want all of this to look like when all is said and done? I want it to look like this. That's what I'm trying to prove. I'm trying to prove that that quantity is equal to this quantity. It sure doesn't look like it yet. Now, a little bit of manipulation of factorials. We know this, that 10 factorial is 10 times 9 factorial. We know that. What if I started with a 9 factorial and I wanted to get a 10 factorial? What could I do?
Put it by 10.
Or something like that? Does everyone agree? This is the direction most of us are very familiar, but what if I wanted to go backwards and beef it up? I could always do something like this. 4n minus 2. Can I think of that as 2 times 2n minus 1? Would that be correct mathematically? Oh, and if I take a 2n minus 1 and I multiply it by 2n minus 2 factorial, aren't I multiplying it by the next integer? In the same way, if I took 9 factorial and I multiplied it by 10, I would get 10 factorial. I've got 2n minus 2 factorial. If I add 1 to that quantity, I'm now at 2n minus 1. So just let's multiply that term and that term, and now my numerator, think of this as one big numerator. Now my numerator is 2 times 2n minus 1 factorial, isn't it? That's my numerator. Now my denominator, clearly I have an n plus 1. but I have an n times n minus 1. What's n times n minus 1? I'm sorry, times n minus 1 factorial.
N factorial.
Wouldn't that just be n factorial? Everybody okay with that so far? And then I still have that term. Now, I want you to look at this part. Let's see, is that? We're almost there. Let me double check something. Nice to remember. Let's make sure I didn't write anything down. And then I got an n plus 1, and an n factorial, and 2n plus 1. And just make sure I didn't mess up anything here. I think we've got all this down. Okay. Okay. Now, let's just look at that part. Just look at that part for a moment. What does that look like?
Two n minus 1 choose n minus 1.
That looks like 2n minus 1 choose n or n minus 1. Does everybody agree with that? I'll write it as n minus 1. That's what that looks like exactly. We're not done, but is that a good thing that it looks like a factorial higher up? That's a lousy way of saying it, but that's kind of what I've got there. Okay? Excuse me. Now, if I keep going, what would I need on top? I need this to be just a 2n. I'm almost there. I really am almost there. There's one more thing I need to do. We said n is greater than or equal to 2. If n could be 0, I can't multiply or do anything with an n. But if n has to be at least 2, would this be a legal step? Okay, if I went like this, n, would that be legal? I didn't say is it the right move. Is it a legal move?
Yes.
Yeah. Well, why would I want to do such a crazy thing? Because what does my numerator now become?
Step up again, 2n factorial.
It's the next biggest term, so my numerator is now 2n factorial. Oh. And this n, when I apply it to here, becomes... Does everyone see that? Then what am I left with? I'm left with 1 over n plus 1 because I used up that 2. Gee, now what? I think that's this. Is it not? Oh, sorry, I lost. I'm sorry, that's n plus 1. Sorry, I can't read my own writing. Okay, so that's this. Okay, now what? We're done. That was my goal. This is Cn. Wow. Factorial manipulations are often tricky. You often have to say, okay, I know what I need. How do I get there? The only clever move we had to do was multiply top and bottom by n. But how have I even known to do that? Because I needed to be a 2n quantity factorial on top. And I had a 2, but I didn't have the n. I can do that because the n was non-zero. Okay? But this is an example of the kind of manipulation that we want to be able to do in general. Is this easy? If you did a lot of these, you wouldn't find this very challenging. But you've not done these before, so it's a brand new thing. It's a different animal altogether. Now, let's get to more of the today's stuff. I just want to make sure that everybody understands this. On the videos for this lecture, I do a lot of these problems. I may have actually done this problem. I certainly did one like it. Again, just to show the manipulation part. Now, I'm going to introduce some notation before we move on. It's simple notation, but it's unusual notation. We know what this means. Right, we know what that is. We now also know, actually I'll use it different. I'll use B this time. we know what this means. This means A1 plus A2 plus all the way up to AN. This one means B1 times B2 times all the way to Bn. Okay. But now if I think of sets, I want you to think of different sets. I'm going to say that AI is a set. I don't care what's in AI. I'm just going to define AI as being a set. Okay? I want to describe then we're going to define unions and intersections of sets much the same way we did sums and products. So what this means, this would be A1 union, A2 union, all the way to AN. Now let me do an example of what that would be. Okay, again, we'll keep it real simple. Let's define A1 as the set 1, 2, 3. Let's define A2 as the set 2, 3, 4. And let's define A3 as the set 4, 5, 6. The notation is important here. There's a tendency to just be kind of lax on notation. You know, some people will use bracket or parentheses or something else. Well, that actually means something very different. If I put parentheses around 1, 2, 3, you guys have all had calculus. What do you interpret that as? Yeah, coordinates in 3 dimensions. Right? It's not a. These are not even similar concepts. They come from different universes. So never start mixing notation because that can be ambiguous, you know, or flat out wrong. All right, I'm defining this. I would like the union from I equal 1 to 3 of AI. So the answer is going to be the union of the 3 sets. So we haven't done much with this. We've used the language. I can do a Venn diagram. That's a really easy way to do this, and I'll do that in a moment. But union. So if I said, I want everybody here to write down their fall classes for me. And now I'm going to take a union of all your classes. Well, what if every one of you signed up, let's say, for Math 255? Do I write 255, 20 times? How many times do I write it? Just one time. So when something occurs more than once, it's an element of the set, but you don't ever repeat the element of the set. So if I want the union of all these, what would it be? Anybody?
1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, 6. Yeah. Even though some of them occurred multiple times, this is what I want. So if I do this as a Venn diagram, I'm a big fan of Venn diagrams, especially when we're defining sets, because it makes a lot of the really abstract stuff we're going to do later on today a little bit easier to understand. I think this one's dying. This one's dying too. Okay. That's not even black. All right. All right, first of all, what's in the middle? Is there anything in the middle?
No.
So, is there anything that overlaps? Let's call this one A1, let's call this one A2, and let's call this one A3. Okay? So, A1 has a 1, 2, 3, but A2 has a 2, 3, 4, so I'd have a 2 and a 3 in here. I'd have a 1 and a 4 here.
No, the 4 is shared.
But the 4 also is shared with a 3. Ah. Now, does that make sense? Does everyone agree with that statement? Now, right now, tell me about the intersection. I think we did this correctly. There's nothing in the intersection. So, without even defining it, I think you guys could all figure this one out. What do you think this statement means in general? I'll do it for 3. It would mean A1 intersect A2 intersect A3. It is the simultaneous intersection. It's not any 2, it's all of them at once. So in this case, what would it be? In words, you'd say it's nothing, it's an empty set. Now, the easiest way to write that would be empty set. Some people like using what's called the null symbol. I've never in my life used it, and I was fortunate enough never to have an instructor in any class I've ever taken use it. In fact, it was the devil. Why? Because it is used probably for 100 different reasons. In other words, it's also the Greek letter phi, which in Calc 3 is extremely important. And in Calc 2 it's important, but it's a different angle in Calc 2. Don't use a symbol. And by the way, having said that, laughingly, at least a third of all the students I teach use it as a zero. Never put a slash in your zero, but about a third of all the zeros I get turned in have slashes in them. And people try to tell me that's what they do in the military. That's not what they do in the military. I know what they do in the military. And it's not putting slashes through zeros. Yeah, when you put a slash through your zero, people say, well, I'm just going to do this, and that will be my... That symbol is used for so many different things. And by the way, every time it's used, it's probably incorrectly used. No, I use an empty set symbol because that's easier. Now, I want to change the problem slightly. Slightly. I'm going to add actually, I'm sorry, I don't want to add a 6. Sorry. I'm going to add a 9. I want to add something that wasn't already there. There we go. I'm going to add a 9. So what does that do to this answer, first of all?
9.
It adds a 9. What does it do to my Venn diagram?
It's 9 in the middle.
Puts a 9 in the middle, and so what does that now do to this answer?
There's a 9 in the set.
It's the set that includes the number 9. The answer is not the number 9. The answer is the set that occurs at number 9, because this one was the set that had nothing. Now, 0 is confusing. If I said, well, but there's nothing there, isn't there a 0? That's something totally different that we're going to talk about later. How many have ever heard the term cardinality? Cardinality. What was the context that you heard?
Gosh, I took linear.
Okay, cardinality, the only time it's ever really used is cardinality is how many elements are there in a set. So if I said, what is the cardinality right now of each of these sets? You'd say all of them have 4 elements. If I said, what is the cardinality of this union? 7. And what's the cardinality of the intersection? 1. So the original cardinality here would be 0. Oh, an empty set has cardinality 0. That's all that term means. That's where there's confusion when I'm thinking of how many elements. That's not what the answer is. That's how many things there are. Can the cardinality be infinite? I could create a situation. I'm going to do that in a moment. All I want to do right here is introduce this notation. There is nothing tricky or confusing about this notation. Okay, nothing at all. Let's define the following. Oops. Let's say actually, I'll write that way. 2 to the I. AI is this, I'm going to define it this way. I could have just put a 2 to the I. So that means that A1 is the set that only has 2, and then A2 is the set that only has 4, and so on. I want to do the union from I equal 1. Let's put a big number here. That's the biggest number I know, bazillion. Could you list all of these? Can you list all of them? Well, that's a lot of things. So how would I write this probably? 2, 4, ... Well, I probably want to put enough that I know what the, is there a pattern? What's the next one going to be?
8.
8.
16, 32, 64.
I could do this, 2 to the, well, 2 to the n, and then eventually 2 to the bazillion. Do you remember what ... means? We talked about this before. If a clear pattern has been established, you continue on that pattern. Clearly, these are double. So in this case here, would I write all of them? No. How many computer programmers do we have here? I used to teach programming way back when. If I have a clear established pattern, can I use a dot dot? When I was teaching Turbo Pascal, it was 2 dots. If I put dot dot and then I put the last one, the program understood all the ones in between. If I established a clear pattern and defined something, I could say something like 1, 2, 3, dot dot 100. And the Turbo Pascal program understood that meant 1 through 100, all of them. I didn't have to actually write them. Why? Because a clear pattern had been established. Run 7 pi root 2 dot dot, no. that no work. You have to have a clear pattern. Now, what if I said, by the way, how many are in here? Well, a bazillion. Can I ask this kind of question? Can this question be asked? Yes. It just means that you're going to do this forever. Now it's an infinite set. Does the order of terms in that set matter? No, but you probably want to write them in the order of the A's, right? A1, 2, 3, 4, because otherwise it's easy to get lost. So all I'm interested right now is the notation. How to do this is easy, okay? So if you're wanting a multiple union, you just take everything, throw it into the basket, and write them all down, okay? That's the easy part. If I want a simultaneous intersection, what do you think the answer is probably the most often for simultaneous intersections?
Empty set.
Probably the empty set, because if I have a lot of sets, then those sets need to contain probably a lot of elements in order to have something that isn't actually in every set. Does that make sense? So the simultaneous intersection, think of the Venn diagrams. I keep drawing circles, overlapping circles, overlapping circles. That simultaneous intersection is probably getting smaller and smaller and smaller. And in real life, most of the time, it's probably going to be empty. That's okay. We're not worried about what it is. I only want to know how to represent it. Finding it's trivial. So I've asked you some questions in this regard. Now I want to move on to the next thing, which is how to do proofs. We're going to do what are called set proofs, or more specifically, element proofs. I want to prove that 2 sets are equal. Now, equal here is kind of an ambiguous term. So I remember way back when I was in college, I got recruited to be on a crew team. Anybody know what crew is? Rowing. Yeah, and so I went to a couple practices. And I said, that's not for me. The practices, we had to get up at 4 because we had to drive to Lake Cachuma, which was about an hour away. I was in Santa Barbara. And then you're on the water by 5. And then after the rowing, then you did your lifting, and then you did your running, and then I was make it back to class by 8, and I realized that's maybe not the best for me. But the thing was, is on a rowing team, you see, I might equal Samuel. And Samuel might equal Zachary. What are we talking about when we're talking about things being equal, you think? If you understand rowing, there is something. There's a maximum amount of weight you can have in the boat. Oh, so in other words, us being equal would mean we actually have the same weight. People are not equal, that doesn't make sense. But the one measurable thing, it doesn't matter how tall you are, it doesn't matter how old you are, it only matters how much you weigh. Weight has to basically be equal. So parts have to get swapped out by equal weights. Now that sounds kind of strange at first, but that's the idea, the one measurable thing. So in the rowing sense, they would call us equal if we were the same weight. That does sound silly. What does it mean for 2 sets to be equal, since a set isn't a numerical value? And it's not the cardinality, because most of our sets are going to be infinite. What do you think it means for 2 sets to be equal?
Sum.
I'm going to keep it simpler than that. I have set A has a bunch of stuff in it, and set B has a bunch of stuff in it, and I want to say A equals B.
We have the same stuff.
They have the same stuff. Yeah, that's what we mean when we say equal sets. We have to define that because that's not a value. Usually we reserve equal, right? It's a quantitative measure. It's an actual calculation. It's a measurement. So if we said we were equal weights or equal heights or equal ages, those are numerical values. Okay? If I have this class roster, and then I was teaching another class and it was exactly the same group of people, I don't say my classes are equal. I would say my rosters are equal. Right? This list of names are exactly the same for the 2 classes. So that's what we mean by the equality of sets. That's very important that we say that. So now when I use capital A, B, and C for a little while, these will always refer to sets. Okay? So we want to talk about containment, first of all. Now, whether you use this symbol or this symbol, I really don't care. The author likes using this symbol all the time. That's fine. I want to say set A is contained in set B. So here's really what we're saying. Now, these are sets. So sets have elements. Let's assume for now that the empty set is definitely the exception. Right? That's something completely unrelated to most of what we're going to do, because we're talking about, I want to talk about the elements of the sets. So an empty set, yeah, that's kind of the exception. So I have an element, let's call it X. What does it mean for A to be contained in B? That this means that if X is an element of A, then X is an element of B. That's what it means, period. If X is an element of B, does it automatically mean X is an element of A?
No.
No, because I could be outside of A and inside of B. So containment means I show that if for every X in A, I prove that that X is also in B. That's what it means to be contained. If I'm starting with given containment, then this is an automatic. If I'm trying to prove containment, then I have to prove this statement. And then I would conclude this statement. So if I wanted to show that set A equaled set B, if I wanted to show that, here's how I show it. We prove A is contained in B, and what do you suppose? B is contained in A. I show containment in both directions. That's the only way two sets can be equal. If A is contained in B and simultaneously B is contained in A, that could only happen if they were the exact same sets. Okay, that's something we're going to do. You don't like this one as much because this one is always exactly twice as much work as doing one of them, because you're doing the entire process literally twice. But we understand there's a process here. Everybody cool with that? So that's a pretty simple thing. Now, with that, we have a few rules and we have some new notation that I want to introduce that's really, really important. And I want to make sure there's a lot of stuff. I want to make sure I get all of the rules and the notations. Let's see. If I was talking about now A union B, make sure I got that. If I define this using set builder notation, we're going to use just generally X will be an element. If I have two elements, I'll call one of them X, I'll call the other one Y. But for now, we'll just say X is an element. Assume, to be safe, it's actually easier to assume these sets are infinitely large. I'm not going to run out of elements. Okay? What does it mean to be a union? That means it's the set of all, it's the set of all X's such that X is in A or X is in B. And this is not an exclusive or. Okay? This allows for the possibility that there is an overlap. X could be here, X could be here, or X could be here. We understand that. For X to be in the union, it's anywhere in here. Again, a common misconception is people want to exclude this. That would not be correct. If I said I have this roster, and then I have another class that I'm teaching later today with another roster, and Samuel's in both rosters, and I said, I'm going to invite anybody who's in the first class or the second class over to my house for the party. So that means we have to exclude Samuel because he's in both. But you say, logically, that doesn't make any sense. No, it really means you're going to get two invitations, doesn't it? It doesn't mean that I'm going to exclude you because you're in both. I'm going to invite everybody in either class. That means I'm going to invite the union of the rosters. So this is what it means. Now, notationally wise, this is not weird or anything else. We often call this the set that includes everything. In statistics, we call it the sample space. Those who've had statistics. The sample space is basically every conceivable outcome. It can be finite, it can be infinite, doesn't make any difference. But it's every conceivable outcome. We understand that. Then I have, well, here's my outcomes. I'm going to flip a coin 4 times. There's exactly 16 outcomes of heads and tails. Your sample space would be H, 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 T, and so on. I am interested in all the outcomes that are exactly two tails. That's called my event. We're going to do this at the end of the course. My sample space had a whole bunch of elements. The particular outcome I'm interested in was something a little bit smaller. Agreed? So A is a set, B is a set, but where do they come from? They come from, we call it big U, the universal set. So the universal set is to sets as the sample space is to statistics. It's every possible thing we are considering. Now this could be, let's say the universal set could be the roster of everybody at Mesa College right now. And A would be everybody in this class. Is anybody here taking a second class? Okay, what's the class?
Computer organization.
Okay, so that's your computer class right here. And this is all students at Mesa College. So these two circles do not encompass the whole campus, do they? My universal set is all the students at Mesa. A is our class, B is your computer class, and you're the only one sitting here in the middle. And that's totally okay. So the union is every X that's in here or here. That should make perfect sense. Because now we can easily define the intersection. And by the way, it is correct. Let me change this slightly. X in the universal set such that. This is how it's formally defined. I think it's kind of redundant. Because if we're talking about things we can't go outside of the universal set, there's no mathematics for that. So it's not incorrect to write it this way, it's just redundant. The universal set is every possible element. I don't really have to say, I'm thinking of a number, and you know, we've only dealt with real numbers in this class. I'm thinking of a number, and it is a real number. Okay, well, if I didn't say anything, it's automatically. Remember, that's the default. Oh, I have to specifically say if it was from the rationals or the irrationals, right? The being in the real number was the automatic default. Remember, we talked about that earlier. I don't actually need to say it. Being in the universal set is at the absolute default. This is correct, but you don't have to say it. You could just say the set of X's. I want to point that out because in the textbook, everything's always prefaced with, it's in the universal set, but it can't be anywhere else. But I could say, I'm interested in the set of the X's that are only in A. I have to say that, or the X's that are only in the B. Does everyone understand? If it's something other than the universal set, I absolutely have to say it. So how would I say this, using the same verbiage? X is in A, and X is in B. And that is huge. I have to be in both simultaneous. Okay, so that's what intersection is. Intersection and union are not the same thing. Not in general, right? Generally, we think of the intersection as being very small and the union as being very big, depending on my sets, of course. Now, notation-wise, we are very familiar with certain notations. If I make a mathematical statement, let's say my statement is P, then how do I negate that statement? What's the symbol we use? We use a squiggle and we say, not P. P is a statement. I went to the store today. I did not go to the store today. There's no elements, there's no sets, there's no numbers. Everybody okay with that? But how do I do the same thing when it's a set? And I want to make sure we understand this because this is fairly simple. So if I'm talking about the universal set, here's set A. You're either in A or you're not in A. But we don't use that symbol. Not in this context. If I said, okay, I have the class roster, that's my universal set now. And I have the folks in this row. What do the rest of you refer to as? There's a term we've used. Everything else, what's the term we use? Remember? It's kind of like you look very nice today.
Compliment?
Compliment. Different spelling. Biff, you look wonderful today. Well, that's a compliment, but that's not the compliment. Compliment means everything else. So in this case, what's out here? We write it that way. Now, it's important that we understand that this notation is not absolute. This is the notation that this particular textbook uses. I like it because there's no way you're going to confuse big C. Does anybody know another notation that's commonly used, particularly like in statistics? Yeah, you sometimes put a bar over the top. And by the way, I hate to say this, but later on when we get to the Boolean algebra, we're going to use a bar over the top instead of a C because we're talking about something different. Now we're going back to statements, but different. Yeah, this is not my favorite thing. So we're gonna have a not, we're gonna have a big C, and later we're gonna have a bar, all kind of meaning the same thing, but it's a context thing. So when we're talking about sets, we're gonna use big C. Not, by the way, not every class will. Some classes will use a different symbol, but as long as we all agree to use the same symbol, it doesn't matter what symbol we use. So big C, when I'm doing statistics, I do bar. Okay, for same idea. So big C is everything else. So how do I define a complement? What is this in set notation? Let's keep it simple. It's the set of all x's, and again, all x's in the universal set, or you can just say the set of all x's such that, and in this context, as you know, set builder notation, the vertical bar means such that. And I like the vertical bar because not only does it mean such that, it separates my thoughts. What comes to the right are the conditions now. The set of x such that what?
Out with it.
That's simple. It's the set of x's that such that x is not in A. That's the definition of a complement. Keeping it real simple there. Now there's one more. This one is a new notation. You may never have seen this one before. Excuse me. I'm interested in those guys. Okay. How many here are not MESA students? You're taking a class, but you're not regular MESA students. Okay, so I have a list. So what I'm going to do later on, I'm going to have a seminar later for all the people that are going to be taking math at MESA next semester. So I want to invite everybody in this class to go to that seminar who will be affected. But if you're not coming back to MESA next semester because you're not a MESA student, I want to exclude you. So I have my set A is all the MESA students. Let's call set B students of a different university, because I know we have USD students, I know we have San Diego State students, we even have UCSD students in this class right now. Okay, I want to only invite the MESA students. These are the MESA students in A. B are the students from other schools. I only want to invite these. How do I say that? This is an odd one. In remedial algebra, okay, in remedial algebra, and again, I want to show because the notations are so similar and we've used different thoughts before. In remedial algebra, I have f of x equals 1 over x minus 1, x minus 2. And I want the domain. Well, we know it's going to be all real numbers except 1 or 2. So normally we'd say, okay, the domain is negative infinity to 1, union 1 to 2, union 2 to infinity. That's absolutely correct. But when you stare at that, do you automatically get the feel for what it is if you look at that interval notation? Because none of you said that. You said all real numbers except 1 and 2. How do I write that? This is my preferred way. This is the formal mathematical way. Does anybody know what the backslash means mathematically in this context? Yeah, it actually refers to deleting. But there's a better notation for that. Because if you didn't know that's what it meant, what if I wrote it this way? Actually, there's a minus sign. Do you think my intent would be absolutely clear now? I have the set of real numbers, and I'm essentially removing that set from the set of real numbers. So set subtraction simply means you're removing those things from the set, okay? I have set A, it equals 1, 2, 3, 4, 5. I have set B, that equals 1, 2, 3. What would the set A minus B then be?
4 or 5.
4 or 5. I'm removing set B from set A. Everybody okay with that? That's actually a formal mathematical term. I want to go back to here because the backslash symbol, which is formal mathematics, is correct. I think the subtraction symbol is even better. Okay? Would you mind taking a peek, Sam, and just make sure that's on? I just want to make sure. Oh, I was going to say, do you see the... Everything looks good. Okay. I'm paranoid about that thing going wonky on us, and I have a Rogue GoPro there. So if I define set subtraction as just simply removing, then what if now I want to do A minus B. Is the answer exactly the same? Some of you are nodding, some of you are shaking, some of you are doing the diagonal. The answer is exactly the same. A minus B simply remove everything from A that is currently in B. But there are things in B that aren't in A. Now look at this picture. Haven't I taken all of set A and removed everything that was in B from my set A? Now, these things over here weren't in A, but these things were. So what is A minus B in this case? Maybe it's more obvious. Wouldn't this be A minus the intersection of A and B? Is that obvious now what I did? Oh, the intersection of A and B is 1, 2, 3. So if I do A minus B, I'm subtracting the 1, 2, 3. I don't care about the 8 and the 10. When I'm doing this, oh, okay, I don't care about the stuff over here. I just want this. So we're going to define set subtraction. So first of all, A minus B is the set of all x's such that, what do you think? Look at that picture right there with the orange. X is in A,
What about B?
but not in B. So I'll say, and X is not in B. Well, wait a minute. If X is not in B, wouldn't this be the same as saying X is in A and X is in X is not in B.
Equal.
I wrote it over here. If X is not in A, then X must be in A complement. So if X is not in B, doesn't that mean that X has to be in B complement? Let's go one step further. All right, didn't I just define, I erased it, didn't I just define intersection a moment ago? The intersection of two sets was you were in both sets at the same time? Don't I have an and here? So wouldn't this be A intersect B complement? Yeah, and this turns out to be a hugely important result. Not because I told you, we just figured it out algebraically. A minus B is exactly the same thing as A intersect B complement. So look at my picture over here. What is B complement? Wouldn't B complement be everything outside of B? Now, everything outside of B, everything inside of A, it's only the orange that's the intersection then, isn't it? Because I'm outside of B and simultaneously inside of A, it's this. So anytime you have set subtraction, this is a correct mathematical statement, but it turns out it might be easier from a manipulation standpoint because we have things like distributive properties and such with unions and intersections. This is kind of cool. I like this one. So set subtraction we're introducing, and that's how we're going to consider that from now on. So as long as I understand complements, then set subtraction is actually fairly easy. So now I want to do an element proof. I'll find it first. Sorry. Hold on. I want to do a De Morgan's law proof because De Morgan's laws are awesome proofs. Now, from a pictorial standpoint, okay, I've represented A union B in this picture, right? I've shaded everything. I would like then to be able to describe the orange part. Now, does it seem reasonable to you that, first of all, I have A union B? Would you agree that the orange part is the complement of A union B? Stare at that for a moment. Hopefully that's, but what would that be? Well, if I took everything outside of A complement, or see, outside of A, which would be all of this, and everything outside of B, which would also be all of this, and I took their intersection, then I wouldn't get anything in here or here, right? Because this is inside A, I only want outside A. So if I took everything outside A and simultaneously outside of B, a little question mark. Does it seem reasonable that I should get that? Just look at my Venn diagram, don't think mathematics. Does that seem reasonable based on what I just said? Does this look familiar? That's De Morgan's law applied to statements. Those aren't sets, those aren't equations, those are just mathematical statements. I have statement P, I have statement Q, and I want the negation of their union. It's the intersection of their negations, we know that. Does this look basically the same in set world? Yeah, so we want to prove this. But I want to show you how to formally do an element proof. There's nothing hard about this, and like all the proofs we've looked at so far this class, it's a structure thing. If I said do a divisibility proof, you know it has a particular structure. If I said do a proof by contradiction, okay, I know I need to start by assuming something. We've done several types of proofs so far, and so far, as a group, we've done really, really well. Now we're going to do what's called an element proof, okay? I want to show, let's show containment in one direction. Because when I do it in reverse, it's going to look really similar. So I want to prove that A union B complement is at least contained in this. So the way I do that is I start with an element from the first set, and I prove that that element is contained in the second set. If every single thing in the first set is in the second set, then the second set is at least as big as the first set. It might actually be bigger, but it's at least as big. So the way we start this is we say, suppose X is an element of A union B complement. Great. That's how we start. What's the last thing I want to say? If I do it right, boom, 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 therefore X is an element of that. That's hopefully my last statement. So, if X is in, then what must be true? Then X is not in what? The union. Do you agree with that statement? If X is in the complement, then X is not in the thing. Okay? But if X is not in the union, this would imply what? X is not in A, and at the same time, not an or, and at the same time, X is not in B. If I said X is not in A or X is not in B, then X could still be in the union. No, it can't be in either one of them, because if it's in either one of them, then it is in the union. Agreed? Oh, so it's got to be. This is a correct use of the implication, and this is the implication symbol we're using now because we're doing sets. I know it's confusing, but now it's the double arrow. But this would imply that X is in a complement, and at the same time, X is in B complement. But I've got X is in A complement and simultaneously X is in B complement. So this would imply that X is in what? The intersection of the two. So far so good? Therefore, I'm done. I have now proven, if I assumed X was in the first guy, I proved that it was in the second guy. So at this point here, we will do the other half, but I want to show you what we've So now I can say, thus, A union B complement is contained. And again, why can I say that? Because I showed that any element in the first set is automatically in the second set. That shows containment, that does not show equality. Gotta be careful on that one. I've only shown the containment. Now, let's do the containment in the other direction. Okay? So now what do I want to start with?
Suppose X is an element of the intersection between A complement and B complement.
Then what can you assume? Or what I've said, not what can you assume, what can you imply or infer? Remember, that means this is the law. I am not proving this. I am saying this is all I know. That's an easy way to think about it. The only truth I know is this, that X is in this. That's all I know. Now, let me take that truth and see where it leads me to. Then, X is an element of A complement, and X is an element of B complement. Agreed? That's what it means to be in an intersection. You got to be in both simultaneously. But then that would imply that X is not in A, and simultaneously X is not in B. Now the first, I'm assuming the first thing, that there's no thought, but the first statement that I have after that is kind of, that's just the definition of an intersection. Agreed? And then the second statement, that's just the definition of a complement. It is correct to put the reasons after. We usually don't. It is correct. If I was writing a big formal mathematical proof, but at the same time you're saying these are kind of simple steps. If you were solving an algebra problem, and I said that, and you say, because I multiply both sides by the multiplicative inverse of 4 and blah, 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 and then using the multiplication property of equality, there's like 5 reasons why this is true. We know that's true. You don't write your reasons next to it. Because why? It's a low-level algebraic step. If I was performing something kind of complicated, I would probably want to say why. Just in case the person reading it doesn't see that I did something really clever and you just didn't see it. But that's the definition. That's the definition. Now, I'm not in A and I'm simultaneously not in B. If I'm not in A and I'm simultaneously not in B, then I'm definitely not in their... I'm not in A and I'm not in B simultaneously, therefore I'm not in their union. If I'm, by the way, I'm not, this intersection would be incorrect. If I'm not in A and simultaneously I'm not in B, then I'm not in any part of either one of them. I'm not in their union. If all I said was I'm not in their intersection, then I'd still be allowed to be in either one of them, wouldn't I? The portions outside the intersection. But if I'm not in either one of them in any way, then I can't be in their union. But if that's true, then what else is true? The next must be an element of... Whenever you're not in something, you must be in the complement. Thus, I have just proved that A complement intersects B complement is contained in that. Now let's finish this off formally. I just showed containment in both directions. So since A union B complement was contained in A complement intersect B complement, and A complement intersect B complement was contained in A union B complement, therefore A union B complement is equal. My goal was to prove equality. Oftentimes, by the way, oftentimes I'm only going to ask you to prove in one direction, because I'm pretty sure if you can prove in one direction, the other direction, does it feel like we just did our steps in reverse? Well, if I did it right, that's probably the correct feel. Now, I just proved a major property theorem. It's not a definition, it's a theorem, but it's really a property of sets, the De Morgan's law. And we're very familiar with De Morgan's law at this point. Okay, this is just a different use of it. Is there another version of De Morgan's law? What if that's intersection right there? then this would be union over here, wouldn't it? Be the other, whatever the other thing is. Everybody good with that? Okay, so what else is true? Well, we have other things, and we've done these versions of these before, by the way. We'll go back to chapter 2. You guys pretty much did a good job on both the quiz and the exam when we were doing the equivalence relations. We had statements. We had P and Q statements. Okay? Now, imagine I replace the P and Q statements with A and B sets. How many of these do you think will still be true? Do I want to guess? Let me give you an example. Write down. Statements. P and Q is equivalent to statement Q and P. That's called the commutative property. This is of logical statements. I have A intersect B. This means logically equivalent. We're not doing logic, we're actually doing sets. So I would use an equal sign. What do you think? The intersection of A and B is the same as the intersection of B and A? That's about as O does it gets, doesn't it? I mean, I drew a picture. Yeah, I'm not changing things. That's the commutative property of intersection. Oh, so there's also one of these. So would there be one of these? A union B and B union A being the same thing? That's pretty much an oh duh also, isn't it? So going back to our logical equivalences, if I replace these with sets, what do you think? They're all true. But the way I state them would be slightly different. What is a tautology?
Something that's always true.
Something that's always true. If a statement is always true, how would I do that in set notation? X is always in the set. And that set better be everything, the universal set. Oh, so in a tautology, you're going to like this, because most of you, I say most of you, because there's always exceptions, but most of you didn't find this all that taxing, especially when you had all the reasons sitting there, and you manipulated things algebraically, right, to get to a point, and you say, why is this true? Oh, I used, the commutative property, or the distributive property, or the negation law, or the identity law, right? We use these things. We know the statements were true. We didn't always know what the reason was. That's why I wanted you to write down the reasons. I knew you could do the right algebra, but a lot of times it's the reason of the statement I don't know. So one of the statements we have this is called the universal bound law. And it has a follow-up. P or everything that's true. Everything's true because it was an or. P simultaneously with it's never true. Then it's never true. How would I do that in set notation? This is I want to make sure that those are sharp angles. You should be able to cut your finger on those things. Never get loose with your notation because intersection and unions are not sharp. What do you think?
Universal.
And by the way, a union symbol is not a U, so don't, the universal set is a U. So if I take A and I union it with the universal set, what should I get? Universal set. If I take a statement and I put it together with something that's always true, I get the always true. So the tautology and the universal set are analogous, aren't they? So how can I read the second one? A intersect something that's never true in set world? If I have the intersection of A and the empty set, what am I going to get? Empty set. Again, see the analogy? And again, it's the same universal bound thing. So there are a few things that fit perfectly with our equivalence relations. And distributive property would be a huge one, obviously. De Morgan's laws would be huge. So those don't change. Now, I don't think, let me check. I'm not sure if they're listed again. They may be. Oh, yes, they are. They are. They are listed. There is one additional one. The set difference. We didn't have a version of, there's no version of set difference when it comes to statements. I don't have a statement with a statement removed. Because that really won't work. So the set difference one, let me double check. I believe in terms of numbers, yeah, there are 11 of the logical equivalences. Those same 11 translate with sets, but then there's a 12th one. The set difference would be the 12th one. Okay, so if you go back and look at your book, you'll go, oh yeah, I see all the same things. I see commutative, associative, distributive, identity, complement, you know. Now, let's do some obvious ones. I have statement P, then I have not P, and I change my mind. It's never not. Okay, haven't you seen it was one of the Shrek movies. Remember when Pinocchio was trying not to tell a lie? You guys remember that? I'm never not there. He was saying something like that. And, you know, as long as he got his right, his nose wouldn't grow. Can I say something totally silly and just keep putting knots in front of it to make it true? Yeah, but it gets really confusing, doesn't it? I'm never not. That means I always am. And we call that the double negation. There was a question, I think there was a question on the exam where you were doing that, and some folks actually wrote they wrote it, others just you went ahead and did it. You know, when you did the negation of something, you just went ahead and did it. That's okay too. That's because that one's so redundant. So if I'm doing something like this, the negation of P and the negation of Q, that's just P or Q. Yeah, technically it's the negation of P as one step, and then I'll do this by the double negation rule. I just do it. I find that one to be kind of redundant. But sometimes it still shows up. How does that work with sets? What would be the equivalent?
The complement of the complement.
What is a complement? That is everything else. So what's the complement of that? It has to be A again. Can't be anything else. Okay? And again, this is referred to as the double negative. Does this come up? Most of the time we just do it. You know, we don't do it as a separate statement. And here's what I mean by that. What is this? This is a De Morgan's law. I didn't put a complement on the B, did I? And you could say by De Morgan's law. Yes, you could say, well, shouldn't I write a complement first and then take care of that? Yeah. But if the complement of the complement is back to here, you know, it's kind of like taking -1 and raising it to a power. You don't do it. I want -1 to the 4th power, so let me first square it, and then I'll square it again, and I'll take those results, and I'll just write the result. You don't do it in between steps. So when you're doing a double negative, just do it. You know, there's no ambiguity on that one. Everybody cool with that? So I want to do a proof. Hold on, I gotta find it now. There's some really, really excellent proof problems. And we want to do them all the way through. I've got to find it. Hold on. Where is it? I can't find the problem I was going to do. It's a set difference problem. My bad. I was looking at my other edition earlier. All right, let's start with an easy one. Okay? Now, this is one where I don't really have to, it's not set containment in both ways. This is more algebra, manipulating something and following it to the end. When you guys are doing logical equivalences, there's two ways to do it. If I said prove, I have something logical equivalent to something else, and what you did, you said, let me make a truth table, let me look at the last two columns and see if they're identical. Sometimes I had a big logical statement and we wanted to show that it whittles down to something small, so you did all of the steps by the commutative property, by the identity law, right? You manipulated it algebraically. You were told, use logical equivalences. Very different goals, right? I wanted to show something was true, one by literally using algebra and the other by using truth tables. A is contained in B. What does this mean? What do I know? Okay, so I'll say, oops, suppose X is an element of A, then this implies what? X is an element of B. That's what it means that's what the definition of containment. A is contained in B means anything in A is automatically in B. But then this implies that X is not where? If X is in B, then X is not in B complement. Which would imply that X is not in the intersection of A and B complement. Why? Because if it's not in B complement, then it cannot be in the intersection. It can be in the union, but it cannot be in the intersection. You with me so far? X is in A. For every X in A, X is not in this. So there's nothing here. So now, if I drew this Venn diagram, it's actually easy. I always like doing this. Big circle would be B. Little circle would be A. Okay? A is contained in B. A, B complement. Is there an intersection between A and B complement? No. So X is in A means X is not in B complement. Okay? Therefore, where does X live? Technically, you can say an empty set. So in other words, the set is empty because there's no X's in it. Now, that's a simple one. That's not, my bad. I could have sworn I had the problem that I wanted to do. I'm having a hard time finding it. All right, let me just grab another one at random. I'm just trying to do one that was just the A's and the B's. Most of them have A, B, and C, which gets kind of complicated. Let us do I would bring these up, but these are short enough I can just write them down. Let's look at, I want to prove, this is, problem number 10. I'm a big fan of drawing pictures. And pictures would always be Venn diagrams in this case. The picture is not the proof. But I'm asking you to prove something, and I always like you to believe it's true first. This picture is going to be a little bit tricky, though. But I want to draw this picture and just see if it makes sense to me. So if I draw this, there's 3 circles, and I should have them intersect, by the way. Is it possible that the intersection of any of these are empty? Is that possible? Sure, but never start by assuming that if you're not told that. You only, yeah, have them intersect knowing the intersection could actually be empty. So that's A, that's B, that's C. So the first one says A minus B. What is A minus B? And here. Does that look right? And what's the second one? C minus B. What's C minus B? It's a different one. Well, that's B, so it would be everybody okay with that so far? What does it appear that my intersection is? You agree? What the heck is that? Well, if I take the intersection of A and C, which is all of this, and I remove B, you see it? Now, so do you believe it's true, first of all? Yeah. What if I do that picture and then, like, no, that's not right at all. Well, that would be more like the determine if it's true. We're not gonna do those. That's just, it gets too difficult. So I have to manipulate this. For me to use properties like commutative property or distributive property, things like that, I have to have everything in terms of unions and intersections. Complements are okay, but it's unions and intersections. I don't have unions and intersections here, do I? So what do I need to do? I need to change this to what? A intersect B complement. That's, remember I talked, that's the definition. I'll leave this in parentheses. And this one's going to be what? Yeah? Now you like this one. Why? They're all intersections. So there's no distributing, does order now matter? Can I manipulate this any way I want? If the first thing intersects the second thing, intersects the third thing, does it matter what order they're in? No. So how about if I rewrite this as A intersect C intersect B complement? Would that be correct? Since everything's intersecting B complement ultimately? A is intersecting B complement, and then that intersection intersecting C, which is intersecting B complement. So everything's intersecting B complement. That basically is using the derivative property in a sense. Now, I have something intersecting the complement. Isn't that the same as saying my something is subtracting B? That's the definition of set subtraction. I'm done. Kind of cool. Here was the key. We believed it. I don't need you to draw the picture. I do that. I always want to be convinced of the truth of the matter. I cannot do any algebraic manipulation from this statement to this statement. You can only do the manipulation when it's unions and intersections. Now, if I had some unions, intersection, unions, distributive property stuff shows up, yeah, that happens all the time. I really love it when I have things like B union B complement or B intersect B complement. I love those. Why? Because B union B complement is what? I think I'll probably write it down. B union B complement, B intersect B complement. These do show up in this kind of context. We love these because the first one is the entire set, the universal set, and the second one, the empty set. We know that. That's kind of cool. Now I'm going to throw a what if at you. Okay. What if A union B is the universal set and A intersect B is the empty set? This is a really important concept. Again, in statistics we do this one a lot. Well, first of all, in this statement, doesn't that mean that A and B are complements of each other? Wouldn't that mean that A is B complement or B is A complement? Now think about it for a moment. Why would that be true? Because together they make up the whole, but they share nothing in common. So I'm gonna put parenthetically, in this case, A would equal B complement and B would equal A complement. That's very important. Okay, but the more important thing is we'd say then A and B are, and the key word is disjoint. You've heard the term disjoint before, and by the way, it always appears in it's called set theory. Going back to statistics, because a lot of this stuff we do in statistics and we use similar terminology, but we don't always use disjoint. Okay, this morning I had eggs for breakfast, and my mother drove to the store. These are two events. These are not sets. These are two things that happen. They're events. I can ask you a probability of an event. But would you say these events pretty much have nothing in common? There's no overlap of anything? So we don't say the events are disjoint. We say the events are mutually exclusive. Mutually exclusive events in disjoint sets are kind of saying the same thing. So let me do it another way. I'm going to flip a coin, 4 times. And what I want you to do is write down all the outcomes. So you have 16 outcomes, heads, 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 tails, and so on. Okay? One event is going to be the event that you got exactly 1 tail. Another event is an event where you get, and you calculate, there was 4 ways of doing that, by the way. Another event, you're going to get exactly 2 tails. There's exactly 6 ways to do that. I gave you 2 different things going on. Is there any overlap? Are any of the outcomes that have exactly 1 tail the same as some of the outcomes that have exactly 2 tails? Are any of these outcomes the same? No. These guys all had 1 tail, these guys all had 2. We'd say the events are mutually exclusive, they have nothing in common. But if I listed the outcomes as a set, the sets would be disjoint sets because the events were mutually exclusive. Does that make sense? So in the term event means I'm actually talking about something that happens, there's a measurable probability of an event. But before you can measure the probability, you need to know each of the outcomes of the event listed in set notation. The sets are disjoint, the events are mutually exclusive. So in statistics, we don't use disjoint on events, we don't use mutually exclusive on sets, but the two go together. So in our term, this is only dealing with sets, so disjoint sets, first of all, have nothing in common. Okay? The disjoint part came from here. But because the union was the whole, A and B are disjoint sets that form a partition of U. That's the key. They are disjoint sets that form a partition. Going back to the coin flip example, I want you to write down all the ways to get exactly 1 tail. I want you to write down all the ways to get exactly 2 tails. Clearly, those are disjoint sets. Agreed? So if I come up with every possible way of flipping that coin, no, I didn't include the no tails or the 3 tails or the 4 tails. Oh, so the union of those 2 outcomes did not give me the whole, did it? It did not give me all outcomes. So 2 sets being disjoint doesn't necessarily mean that when you put them together, you have the whole. It's if they're disjoint and putting them together, they have the whole, then we call them a partition. Well, but they're just complements. We already know that. Yes, but that's only if there's 2. What if I have many sets? So let me do another one. What if I have the following? I have the sets A1, A2 through AN. I have N sets. And what I would think about is every one of these sets I want to be disjoint, and I want all the sets together to make up the whole. So let's keep it really simple. In the terms of the coin flip, one set will be all the outcomes that have 0 tails. The next set will be all the outcomes that have 1, then the set with 2, the set with 3, the set with 4. I'd have 5 different sets, wouldn't I? Would any of those sets contain the same outcomes? No, because the set that had 4 tails was tails, 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 tails. The set that had 0 tails was heads, 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 and so on. There would be 5 different sets of outcomes. Clearly they're all disjoint, but if I put them all together, I'll get the whole. Oh, so if there's only 2, it's easy. They got to be complements. But if I have more than 2, there's no complements going on here. None. So now here's what I want to say. the union from I equal 1 to n of the AIs I want to be the universal set. And at the same time, the intersection of the AIs, what do I want it to be?
The empty set.
The empty set. This term means they're disjoint. Disjoint goes from here only. Has nothing to do with that piece. They're disjoint, but together they make the whole. If both of these are true, then these guys form a partition. Partition. Does that make sense? With two, it's really easy, but what if I have more than two? So I have a whole bunch of sets. If I drew it as a Venn diagram, there's no intersections. All my circles are separate. But as a Venn diagram, they make up the whole. So a better Venn diagram in that sense would not be circles. No, a better Venn diagram would be something like this. Right? Now clearly, I'm drawing it so everything A1 is here, everything A2 is here, and so on. There's no overlap, but I filled up the entire set. So a partition literally can look like that. Okay, so there's no overlap, but together they make up the whole. And that's really important. When we get to the probability later, that becomes a problem because when there are intersections, those who've done any form of combinatorics, any form of counting, when I have intersections and I'm trying to figure out how many outcomes there are, I want to count all the people in this class and then all the people in your computer class and add them all up, and that's how many students we have. Is that right? No, because I double counted you, didn't I? Oh, I have to then remove the intersection, don't I, in order to make sure I don't double count. That's complicated. It'd be much easier if I took sets that had nothing in common. Then I could just add them up easily, couldn't I? That's the idea here. If my sets have nothing in common, but together they make up the whole, that's actually the best kind of situation. You don't have any control over that, but those are just definitions. Okay, any questions? The element proof part is going to trouble you at first because you've never done anything like that. Please look at some of the examples in the book. They're really well stated and they're really easy to follow. And you're just doing what we're doing. The hardest ones are ones like this that have the subtraction that you convert. But then from that point on, it's usually fairly simple because we already know most of the algebraic rules. Okay? All right, let's go ahead and stop that.